So linked list cycle. Given the head of a linked list, determine if the linked list has a cycle in it. So a cycle in a linked list is if some nodes can be reached again by continuously following the next pointer. So in the example here, the node 3 points to node 2 and node -4 also points to node 2. That means we have a cycle in the linked list. In which case we're going to return true. This example, we start off with the node 1 and then we point back to the node 1. So again, there's a cycle in the linked list. And in example 3, we only have one node. A single node means there's no cycle, so we return false. So the linked list cycle detection algorithm is called Floyd's cycle detection algorithm. And how it works is, again, a two-pointer approach. Basically, we have a slow pointer and a fast pointer. We set them both to the head, the start of the linked list. So while fast and fast.next, so we need to make sure fast.next is not null because we need to call fast.next.next. So fast equals to fast.next.next and slow equals to slow.next. So Floyd's cycle detection algorithm checks that having one node go faster than the other, it checks if these two nodes ever converge onto the same value. So if slow equals to fast, that means we found a cycle in the linked list and we return true. Otherwise, we return false. So why this works is because one node always travels one faster than the other. So the fast node always catches up to the slow node if it's behind it. And because there's a cycle in the linked list, we're never going to exit the linked list. Fast and fast.next is never going to equal null because they're going to always be cycling in the cycle. So if one always travels faster by 1, so fast is going to catch up to slow by 1. So a little bit at a time, eventually slow is going to be caught up by fast and they're going to converge onto the same node. So slow is going to equal to fast and we're going to return true because then we just detected a cycle. However, if fast or fast.next becomes null, that means we ended the linked list. We found a pointer null. If there's a pointer null, that means the linked list does not have a cycle, in which case we return false. So let's try submitting that. Nice, okay, that worked. So this question is very classic and Floyd's algorithm is good to know. So moving on to the next question, number. Given an array integer nums containing n+1 integers where each integer is in the range 1 to n inclusive, there's only one repeated number in nums and we want to return this repeated number. So we're going to want to solve the problem without modifying the array of any type and also using only constant extra space. So in example 1 here, the duplicate number is 2, we're going to want to return 2. In example 2, the duplicate number is 3, we return 3, and in example 3, it's all 3s, so we're going to return 3. So this question is an extension of Floyd's cycle detection algorithm, where we have to not only detect the cycle, but also the start of the cycle. So because there's two numbers 2, they're going to both point to the number at index 2, which is the 4. So we want to return this number that's pointing to this index 2 times. So first, let's start off with just writing Floyd's cycle detection algorithm on an array. So the slow pointer, instead of calling next, it's going to be nums 0. So this is the start or the head. Fast equals to nums at 0 as well. So while 1 is just while true, fast equals to fast nums, should be nums fast. So what this does is that it calls nums fast 2 times, basically fast.next.next, but in an array context. And slow equals to nums slow. So if slow equals to fast, this is the same as the previous question. If we encounter something that is equal, we want to break out of this while loop. So this question guarantees that there's always one repeated number, so we can use a while true loop and then break out when they're equal. So Floyd's cycle detection algorithm tells us, this algorithm is probably worth a video of its own, so we're just going to skip to the result of the algorithm. So this is what our array looks like. So 1, it points to the number at index 1, which is 3, which points to the number at index 3, which is 2, which points to the number at index 2, which is 4. And then the 2 and the 4 repeatedly point to each other, so that's the cycle. So the result is saying that the distance from the head of the array to the start of the cycle, so in this case 1 to 2, let's call that distance x, and the distance from the point the two pointers merge, which is this 2 here, to the start of the array is the same. So let's call that y. So Floyd's cycle detection algorithm tells us that x is equal to y. So to use this fact, we can move one of the pointers to the head of the array. So let's call them P1 and P2 for the 2 pointers. P1 equals to head, and P2 is just going to be slow. So slow is where the 2 pointers converged. So what we know is that to go from the point where the 2 pointers converged to the start of the cycle is the same as the distance from the head to the start of the cycle. So x in this case, we're going to go from 1 to 3 and then to 2. So x is equals to 2. And we can see y equals to 2 as well, because 2 goes to 4 and then back to 2. So now they're both at 2, and we want to return the answer, which is that 2. So we don't have head here, so it should be nums at 0. So while P1 is not equal to P2, so while these numbers are different, 2 and 2 have not met yet, so P1 equals to nums P1 and P2 equals nums P2. So now P1 and P2 are going to eventually merge. They're going to be the same number, so we just want to return either of them. And this is guaranteed going to happen in this question because the question says there is one repeated number in nums. So nice, that works. I'll probably make another video explaining Floyd's cycle detection algorithm and how we got this equation that these 2 distances are the same. But that's probably out of scope for this linked list question. Let's try submitting that. Nice, that worked. So moving on to the next question. LRU cache. So in this question, given a data structure that follows the constraints of a LRU cache, we need to implement these 3 functions. So the init function to create a LRU cache with positive size capacity, a get function to get the value of a key if that exists, otherwise we return -1, or a put function, which updates the value of the key if the key exists, otherwise we should add the key value pair to the cache. And if the number of keys exceeds capacity, so if there's more keys in the cache than we can have, we should evict the least recently used key. So in this data structure question, we basically need to keep track of all the keys as well as the one that is the least recently used. And we should always be pushing that least recently used towards one end. So a common way to represent this is with a doubly linked list, with one side being the most recently used, or MRU, and the other side being the least recently used, or LRU. So with any linked list question, we don't have a list node here, so let's actually create that. So class node, we should create an init function for this. What we take in a node is a key and a value. So the key is what's put in and the value is what is stored. So let's create a key value. So we're going to set these default to 0 because we're going to need the 2 sides of the LRU cache, and those are going to be initialized to empty nodes. So we can just pass them as empty nodes. So self.key equals to key and self.value equals to value. So other than that, in a doubly linked list, each node also has to have a left pointer and a right pointer. So self.left equals to none. Let's create them as empty for now. And self.right equals to none. Nice. So now we have a linked list node class. And to create the LRU cache, we should have one being on the left side, being the least recently used, and the other one on the right side being the most recently used. So let's draw out a quick diagram here. This is our data structure. We're going to have LRU on the left side. It's a doubly linked list to a node, to another node, let's say one more node, and then the MRU side. So at the start, when we create a empty LRU cache, it's going to look like this. LRU directly points to MRU. So with that, we can start creating the init function. So self.lru equals to an empty node and self.mru equals to an empty node. So this is setting up the empty LRU cache data structure. Now we should point the left LRU to the MRU and MRU to the LRU. so they're doubly linked. So self.lru.right, because MRU is on the right side of the LRU. Self.mru and self.mru.left equals self.lru. Just so it's symmetric and the left and right pointers are pointing to each other. We also need a variable to store the capacity. So self.capacity equals to the variable passed in capacity, and self.map equals to a dictionary. So what this map does is it maps the key that we're calling to get for get and put to the node inside the cache. So after that, we're calling the get function. So there's two cases with the get function. There's one where the key exists. So we want to return the value of the key if it exists. Otherwise, we want to return -1. So if key in self.map.keys, so we're checking if this key is in the cache. If it is, then the value is going to be self.map@key. So this is the node. To get the value of the node, we're going to call .value. And then we're going to need some helper functions. Let's just create them here. Def. We're going to need one to remove an element from the cache. So def pop. And then we're going to remove it at key, and also another helper function called def push key value. So what pop does is that it removes the element with the key, and push pushes a new element with the key and carrying the value. So if the key is in the map, that means it's in the data structure. So we're going to get the value, and we're also going to remove, like pop it and also push it. This is a simple trick just to push the node back into the LRU cache to indicate that it's recently used, because get is using this element. That means after getting an element, the node with this key should be at the top of the LRU cache, basically the most recently used side. It'll be this node right here. So to do that, we're using this trick with self.pop. So we pop it out and then we push it again. So self.push key value. So after that, we can just return the value to return to the user the value they asked for. Otherwise, if the key is not in the map, so the key is not in the LRU cache, we're going to return -1 like the question wants. So that's the get function. So with the push function, there's also different cases. So first, let's say the key is in self.map.keys. So if it's in the key, we actually want to replace it with the new value if the key exists. So we want to pop out the old value, self.pop key and self.push key value. So we're updating the value of this node with the key. So another case is if it is not in the map, then we want to push it. If we want to push it, so let's suppose there's still capacity. So self.capacity is greater than the length of self.map.keys. So there's still capacity to push more things onto the map, more things onto the LRU cache. So we're going to just push it, self.push with key and value. We're going to code up the pop and push functions in a second. So otherwise, we have no capacity. So what do we do if there's no capacity? We want to pop out the least frequently used element. So self.pop, which is the least frequently used element, it's the one on the right side of LRU. So this node I highlighted right here. So to get this key, the key of this node, it's going to be self.lru.right because it's on the right side of the LRU, and .key to get the key. After that, we can push in the new value just like before. So self.push key value. And this doesn't return anything. Cool. So with those out of the way, we can try to code the push and the pop functions. So let's start with pop. First, we need to know which node we're popping. So node is equal to self.map@key. So key is guaranteed to exist because all the instances where we use pop, we're popping that specific key from the map and from the LRU cache. So it's going to exist. Let's define the left node. So the left side of this node we're going to pop is node.left. Right node equals to node.right. And the reason we need the left and the right nodes is because we need the neighbors to start to point to each other. So the left node is going to point to the right node, left node dot right. Sorry, it should be node dot left. So the left neighbor, new right neighbor is not going to be node, but it's going to be the right node. Node dot right dot left equal to left node. So essentially we eliminated this node from being in the cache. And what we need to do after is self.map.pop. So pop removes this element key and the value associated with it from the map. So the size of the map is going to decrease by 1. So now we can do the push function. So what do we need in the push function? We need to create a new node. So node equals to node key value. So this is the node data structure that we created up top here. So with this new node, let's call the previous self.mru.left. So the previous most commonly used element is going to be our left neighbor now. So previous.right equals to node and self.mru. And now the new left node of the MRU is going to be our new node. So to create the neighbors of our node, node.left is going to be previous, like I just said, and node.right is going to be MRU, because this node is going to replace it, the previous most frequently used node, and then stay here. So after that, we should add it to the map. So self.map.key equals to node. So with that, let's try running it to see if it works. So we're passing in too many values to self.push. So 3 were given, because for push and pop, we need to pass in self as well because it's a method of the class. So that's just a Python thing. MRU is not defined. MRU should be self.mru. Nice, that works. Let's try submitting it. Cool. So this question, the trick is realizing that it's actually a linked list question because it's not very apparent from the description. We need to realize that we can create a doubly linked list to represent the LRU cache, keep track of the least recently used node and the most recently used node, and we should pop and push at appropriate times just to make sure our node is always going from least recently used to most recently used. So that's it. This is actually a rather tough question. Let's move on to the next one. So merge k-sorted lists. So we're given an array of linked lists with each linked list being in sorted order. So merge all the linked lists into one sorted linked list and return it. So immediately this question is very similar to the question we've done before, where it's merge 2 sorted linked lists. So instead of merging 2, we're going to merge k. So a way to change k back to 2 is by constantly dividing the list of linked lists into 2. So kind of like a merge sort approach, where we split the number of lists we need to merge in half, merge the left half, merge the right half, and then merge the 2 left and right halves together to get our final answer. So to code this up, we should use our previous function defined as merge 2 lists later. So def merge 2 lists, L1, L2. We can copy this over later. So to deal with merge k lists, let's deal with the edge cases first. So if the length of lists equals to 0, so if there's nothing to merge, let's just return none, as in null pointer to the head of the final linked list. Otherwise, if there's only one linked list to merge, then we should just return it. So if length of lists equals to 1, return lists at 0. So otherwise, we should divide the k lists into half, merge the left half, and merge the right half. So let's create a half variable equal to len lists divided by 2. So the left half, this is going to be self.merge k lists from 0 all the way to half. And the right half is going to be self.merge k lists from half all the way to the end. So we could just not put anything at the end. This just gets us the remainder of the lists. This is the Python syntax, and after that we can just return merge 2 lists because we simplified the k lists into 2 lists now. So merge 2 lists, left half, right half. So let's go to the previous function that we did earlier, copy over this here, and put it here. So let's deal with the indent, and that should be it. So we dealt with the case that there's no list to merge, the case that there's only one, and the case that we're merging more than 2, or 2 or more. So this is called list 1, and this is called list 2. So cool, that's accepted. We're basically taking advantage of a previous function that we've done and simplifying our question into that function and then returning the answer. Nice. So this runs in O of n log n time because it is a merge sort approach. So moving on to the next question, reverse nodes in k group. So given the head of a linked list, reverse the nodes in the list k at a time and return the modified list. So k is a positive integer that is less than or equal to the length of the linked list. If the number of nodes is not a multiple of k, then the left out nodes in the end should remain as is, so they're not reversed. So we can't alter the value of any of the list nodes, and the nodes themselves should be changed. So basically we want to rearrange them so that we are reversing them k at a time, but then keeping the relative order of the groups the same. So this question again reminds us of a previous question we've done called reverse linked list. So we should be able to take advantage of this reverse linked list somehow. But first, so let's call reverse with head. So this is our helper function that's going to reverse a linked list. But first we need to find out how big of a group to reverse. So we want to group it k at a time, which means we need the pointer to the head of the next k group. And also that means we need the end of our k group. So let's create a pointer pointing to head. We want to move it down k minus 1 times because we want the last node in our k group because we're reversing and returning that one. So pointer equals to head for I in range k minus 1. So we're moving pointer down k minus 1 times, pointer equals to pointer.next. So next head is the head of the next k group. It's going to be pointer.next. And we should set pointer.next to null so we don't have any cyclic linked lists. After that, we should reverse this. So let's create the actual head of our linked list should be the reverse of the 2 here, which is going to be what pointer is at. So head equals to reverse head. Basically we're reversing the linked list, the blue linked list here, 1 to 2, it's going to be reversed into 2 to 1. So now we need to connect the end of the reverse linked list. The end is now 1, we need to connect the 1 to the next head, and then reverse the next k group. So we can do this recursively. So to get the 1, we basically need to traverse the now reversed blue linked list and k minus 1 times. So let's assign pointer to the head again. So this is the head of the reversed linked list. So move this down k minus 1 times again. Pointer equals to pointer.next. So now we want to connect the blue and the red linked lists. So pointer.next equals to self.reverse k group. So we can call reverse k group to reverse the next group of k nodes. So next head, and it's starting with next head, which is 3, it's the start of the next k group. And we should pass in the parameter k. So after that, we should just return head. So we need to copy over this reverse function from the first question. Oops. So now we have our helper reverse function, and one more thing is that if we reach the end of a linked list k group while we're iterating down k-1 times, we should just not reverse this group. So if we don't reverse it, then we're just returning the head. So if pointer equals to none at any point during the traversal, we should return the head, and this means we're basically not reversing anything. So let's try running that. So I think I spelled this wrong. Okay, there's no R in reverse. Nice, that worked. There's no R at the end of reverse, sorry. And we can try submitting it. So this question runs, so what's the error here? Oh, where k is 1. So if we keep calling reverse k group recursively and k is 1, we're eventually going to call reverse k group on an empty or non-list node. So we just need to do an edge case check here. If head equals to none, we should return none. So let's try submitting this. Cool, okay, that worked. So this question runs in O of n time because we're splitting the entire linked list into n divided by k different groups, rounded down. So each group has to get reversed, so that takes O of n divided by k time. And because there's k groups, we multiply that together, so it's going to be O of n time in the end. So thank you guys for watching this video. Hope you guys were able to learn something, and I'll see you in the next video.